Hey you, let's talk about specific heat capacity. For this one we got two learning targets. First one's that you can define and understand what specific heat capacity is and describe it to someone else. And the second thing is you can determine what the specific heat, energy output, temperature change, or the mass is using our temperature change equation. So we'll get to that in a minute. Right, so heat and thermal energy. So assuming that you guys remember how temperature change works, how the difference between heat and temperature. If you don't remember, I want to go back and look at those slides, that video from a little while ago. So a little quick catch up on it, but not the full details. Heat is our total amount of kinetic energy in the substance, whereas temperature is just the average amount of the particles. So some might be higher, some might be lower. They average out to have your temperature, but the total amount of all of them is your heat. Both heat and energy, they're basically the same thing. They're measured in joules and sometimes in calories. So kind of like the calories in your food, except calories in our food are technically kilocalories, so it's actually 1,000 times more actual energy calories are in your food. So you calculate, someone says, oh, it takes more calories to digest celery than it does when you actually eat it. That's not true, because one's talking about the actual chemical calorie, one's talking about the kilocalories, 1,000 times that. One's talking about how much it takes to digest it. So make sure you're looking at the right units. One's a little c, one's a big C, which stands for kilocalories. FYI, a joule is not that much energy. So when we talk about a joule, oh, it's 10 joules. That's not that much. You have to have lots of joules for it to be much energy. So if you have 100 milliliters of water, which is, I don't know, this much in a cup probably, you take it from room temperature to boiling, you'll take 33,000 joules. When we start getting those big of numbers, we're usually talking about in kilojoules. So 33 kilojoules of energy. That's how little energy it takes in each one. Taking just a little bit of water to boil it, it's 33,000 joules. And guess what? If you don't remember, there's no such thing as cold. We only have heat. Even though we talk about cold, it's a very common term, it's very handy for us, it's not a real thing. Alright, so specific heat capacity. The actual definition is the amount of heat it takes to raise 1 gram of something, any substance, by 1 degree Celsius or Kelvin. Those scales are the same, right? They're off by 273 from each other. So 0 Celsius is 273 Kelvin, 1 Celsius is 274 Kelvin, each go up by the same increment together. So how much heat or energy it takes to raise 1 gram of something 1 degree Celsius. So every substance has its own set thing, kind of like density. Iron has a set density, never changes. So does aluminum or glass or water or gold. They all have a set density. They also have a set specific heat capacity. How much heat is required to raise up a set amount of substance 1 degree Celsius. So 100 grams, two different substances, they'll take a different amount of heat to raise them up 1 degree Celsius. So look, the units are joules, that's per gram per degree Celsius, or written that way. So every joule, how many joules it takes for every gram to go up 1 degree Celsius. So the actual heat equation you'll use is energy, which is E or Q sometimes delta H. So look down here, the red. There's 3 ways of writing energy or heat. And it equals mass of the substance. C stands for specific heat. Sometimes it's put as CP, specific heat capacity. And that's found for you guys, for you in my class, on the back of your green periodic tables. Probably green, for common substances. And then T2 minus T1 is going to be your change in temperature. So it's the final temperature, your second one, minus your first temperature. So make sure you know what those are, how to use them. The common one you might want to just keep in your minds that water specific heat capacity, the one used most often, is 4.184 joules per gram degree Celsius. Okay, then let's try one. How much heat or energy in joules must be used to raise the temperature of 180 grams of tap water from 15 degrees Celsius to 96 degrees Celsius? All right, so what do we have? We need our heat equation. So E or Q or delta H, any one of those, is going to equal MC, we call it delta T, which means the change in temperature, T2 minus T1. So our mass is 180 grams from the question. C is the specific heat of water, which gave you on the last slide, or it's on the back of your periodic table, or you can Google a chart of them also. And our final temperature was 96. Our initial temperature was 15. So we subtract them, we'll get 81 degrees Celsius. When we multiply them all out, grams will cancel, bottom here, top here, Celsius on the bottom there, and top here. We'll have just joules. So we should get 61,002.72 joules, or since it's a big number, we usually put in kilojoules, so 61 kilojoules of energy. That's how much it'll take to take that much water and raise it up 81 degrees Celsius. Hopefully fairly straightforward. If not, let me know. Another one. If that last one made sense, try and give this one a shot. Pause it. Hit play when you think you got it or when you get stuck. Okay, so a copper sample with a mass of 0.312 kilograms is at 990 degrees Celsius. The sample is placed into water and cooled to 210 degrees Celsius. How much heat energy was given to the water? Specific heat of copper, also on the back of your periodic table, is 0.385 joules per gram degree Celsius. Make sure you check your units because they won't all match up right now. So first we got to get kilograms to grams, because this is in kilograms, this is in grams, they won't cancel right now. So converting, there's 1 kilogram is equal to 1,000 grams. So those cancel, we get 312 grams. Now the units match up, we can put it in the formula. So E equals 312 grams times 0.385 joules per gram degree Celsius times T2, our final temperature, minus our initial temperature, and we'll get, well, negative 93,693.6 joules, or negative 93.7 kilojoules. Wait, negative? How can we have negative heat, negative energy? Well, can you lose heat? Can you lose energy? Yeah. It's just getting colder, which isn't a thing, but it's losing its heat. It went from 990 degrees Celsius to 210 degrees Celsius. That ought to be getting colder or losing energy, losing heat. That one should make sense, hopefully. Let's solve for something else. Alright, so if you put 2,700 joules of energy into a 300 gram piece of wood, how much would its temperature increase by? So, same equation, but now we have the energy, so we have this variable, we have the mass, which is the 300 grams, we can find its specific heat on our chart. We don't know the change in temperature, so we need to solve for that one and get T2 minus T1, delta T, by itself. So to rearrange, you get T2 minus T1 is equal to Q divided by MC. So we divided both of these, M and C, to get them on the left side of the equation. So plug in all the other variables. Take 2,700 divided by 300 divided by 2.5 joules per gram degree Celsius, the specific heat of wood. And we should get an answer of, it goes up by 3.6 degrees Celsius. So 2,700 joules only raises it 3.5 degrees Celsius about. That's all it is. Joules don't do a whole lot. You need a lot of them to make a big change. Okay. Then, jumping on to the other way we use this a lot. So, calorimetry is a big fancy word that really means just measuring heat. So a very common thing that you'll do in private lab on this will be measuring the heat lost by one thing to try and solve for another piece of what it has in it, another variable about the substance. So let's look at an example here. We have a styrofoam cup is a really good insulator. So we put water in here, and we had a really hot piece of metal. So we don't know what that metal is, We measured it before. We know it's 130 grams. And we heat it up to 95 degrees Celsius. And we place it in that styrofoam cup with water. And we know how much water is in there, 250 grams. And this is the temperature of the water, room temp. When the hot metal's in the water, it's going to lose the heat. It's warmer than the water. So the heat always goes from hotter temperature to a lower temperature. When it does that, the heat that leaves the metal all goes into the water. And it heats the water from 21 degrees to 25.2 degrees Celsius. Now, when the metal cools down, loses its heat, it's also going to be at the 25.2 degrees Celsius. There has to be at the same temperature at the end. It can't stay warmer. It's going to keep losing heat until it's the same temperature as the water. They meet there in the middle. So the question would be, what is the specific heat of this metal? And therefore, by that, we can determine what metal is it. Okay, so if we know that all the heat lost by the metal went into the water, that means that the energy equation for the metal or the water, so mc delta T, the change in temperature, that energy that was gained by the water has to be equal to the energy lost by the metal. All the metal's energy that was lost went into the water. So energy of the metal equals energy of the water, but on the opposite side. So therefore, the mass of the water times the specific heat of the water times the change in temperature of the water also has to equal the mass of the metal times the specific heat of the metal times the change in temperature of the metal. Let's go back to the problem. So we have our problem, and so if we know that down here number 1, the mass times the specific heat times the change in temperature of the water has to equal that of the metal, and we know the mass of the water, we know the specific heat of water from our charts, or you might have it down by now, times the change in temperature of the water, the 25.2 minus the 21, is got to equal the mass of the metal times the change in temperature of the metal, which this one will be negative now, because it's losing heat. The only thing we're missing is C, the specific heat of the metal. But now we're down to one variable. We can solve for that one variable by dividing our left side by 130 grams, and whatever 25.2 minus 95 degrees Celsius comes out to. Oh, looks like negative 69.8. Remember that negative means it lost heat. When we solve that math out, we get to 0.48. Yeah, so the specific heat of the metal equals 0.48 joules per gram degree Celsius. You'll get a negative value, but it's not supposed to be negative. It's just that's it from the loss of heat. So if you had a specific heat chart available, like one on the back of your periodic table, and this is the real problem, the real metal, it should be close to one of those. You can say, oh, that looks like it's iron, or that looks like it's lead, or silver. That would tell you what the metal is. It would tell you its identity based on that specific heat property of the substance. Hope that makes sense. If not, ask me some questions.